Space, a frontier. These are the voyages of the YouTube channel smAsho, as well as the Twitch stream smAsho. It's our cosmology segment. We streamed it live to Twitch. Shout out to our Twitch viewers. First thing we're going to talk about is magnetic fields. And what you're looking at here is the relativistic jet of the famous, quote, supermassive black hole, and quote, known as M87. And what you're looking at here is light polarization of the material in the galactic jet. And what's conspicuous about this that you may realize right away is that we see magnetic field force lines in this direction and also in this direction, and perpendicular to them. Doesn't that seem a little strange? How come the magnetic field lines are in such an orientation? Does it have to do with things like electromagnetism? Is it an example of plasma cosmology? In effect, well, it certainly is. The title of this article is Magnetic Structures Detected Around Galactic Jets. Now, this study is about many galactic jets, and you can see the differences in different galactic, wavelengths here, such as the ALMA and the VLBA and the EHT. Different wavelengths of, that's like the microwave spectrum there, gigahertz radiation. Yeah, radio astronomy, folks. Quote, we are now seeing the next crucial piece of evidence to understand how magnetic fields behave around black holes. As there are relativistic protons, mainly hydrogen nuclei, blasting out of that black hole, it is a likely source of cosmic rays, which are primarily also comprised of hydrogen nuclei, otherwise known as protons, similar to the protons that are constantly blasting out of the sun. Now, M87 is believed to be about 6 million solar masses, and I don't really need to argue that very much. I just try not to use the term black hole. I prefer to use the term massive radio source, a term which I noticed during the mid-90s was being used by about half of the astronomy community, and there's a distinct reason for it, as we can measure the radio data from it. However, some of us prefer not to call them black holes, as black holes are, to many folks, a bunch of math seeking out observations. Anyway, if you want to read this one, there's a link to the paper on it as well. You can find it at SciTech Daily. Title is Magnetic Structures Observed Near Supermassive Black Hole, talking about M87 and its jets. And in the paper, you'll find more similar jets with similar types of structures. If you've got any theories as to why these are like perpendicular to each other, how come these are at such a strange angle compared to these? Is this not just a jet in which all the particles are moving in this direction? Well, certainly not. I would say it's highly unlikely that they are. But if you have a theory of it, leave us in the comments what you think about that. Today's random number is 872, which coincides with an interesting object indeed at the Neil Gehrels Swift Bat X-ray Observatory. If you come down to number 872, you will find a millisecond pulsar. Yes, a pulsar with a periodicity in the milliseconds, known as HT 1900.1-2455. It's also known as HETEJ 1900.1-2455. Here are the hard X-rays that come out of this pulsar, and it's an interesting radio source indeed. You can see this one's actually gone into a lessened energy state here. Less X-rays coming out of this in the past like 6 years, as this is the 16-year graph of the hard X-rays from that millisecond pulsar. And here you can see it's been quite consistent over the past 30 days. Let's take a look at this in some wavelengths. So first of all, we're going to look at this in the BAT survey. And this particular survey is a 70-month all-hard X-ray survey. So this is the Milky Way disk right here, folks. As you can see, all those X-ray sources lined up around the galactic plane. And we'll zoom in on this X-ray source. this millisecond pulsar, and view it in some other wavelengths. So that's hard X-rays. And here is ultraviolet light. So we can see if we can see any plasma structures associated with it there. Maybe some sort of a nebular cloud there. Some features looking like they're showing up there in ultraviolet. So that's interesting. Let's continue down the electromagnetic spectrum here. Let's see what Pan-STARRS shows in optical. And perhaps some optical structures being revealed. You can see that bright blue spot there associated with that millisecond pulsar. Perhaps some stars associated with it as well. Hard to tell if they're in the foreground or if they're part of the same structure. So let's take a look at it on the 2 mass as well. There's infrared at 1.66 nanometers. There's 1.23 nanometers, 2.16 nanometers. And there's the Colorize survey from the 2 mass. And let's just take a look at some radio here and see if anything shows up. No promises, folks. I'm just looking at this for the first time. Let's just go back to X-ray here. I don't want to spend too much time looking at the millisecond pulsar. Anyway, it's a very bright X-ray source, and there may be some structures associated with it. If you want to look at it yourself, head to the CDS portal. It's known as HETE J1900.1-2455, a catchy name. And the CDS portal is fantastic in that it shows you the spectral data. There's where it lines up in terms of wavelengths. And tons of articles about it, tabular data, etc. The millisecond pulsar, number 872, at the Neil Gehrels Swift X-ray Observatory. And check out the astronomy picture of the day. It includes an open cluster, similar to a globular cluster with about 1,000 stars, and a supernoval-like shell remnant located in the constellation Cassiopeia. This spectacular bubble-like shell here that we typically see associated with various nebular clusters, supernoval remnants, etc. The bubble in the star cluster. So that's the open cluster is known as M52, Messier Object 52. The bubble nebula is known as NGC 7635, the new general catalog. And the cluster is about 25 light years across. And M52, this open cluster here, is located at about 5,000 light years distance, fairly close to us in the Milky Way galaxy. Let's continue on. By the way, if you want to read more about NGC 7635, there is a link on the astronomy picture of the day. Again, that's at apod.nasa.gov. That link takes you to this. The O-type star link will take you to this article about the wind-blown nebula NGC 7635 from the new general catalog. Let's talk about radio frequency. This is the pinwheel galaxy, folks, and you may be able to see some sort of a little bit of a spiral-like structure here. And it's because what we're looking at here is hydrogen and the redshift of it. So what's interesting here is that these portions up here are moving toward you, the observer, and these portions down here are moving away from you, the observer. And this area here is fairly neutral, indicating that this object is rotating. And this object is, again, the pinwheel galaxy M33. There's a lot of hydrogen in the universe, and the hydrogen gives us insights into the structures associated with the hydrogen, obviously. One of the many reasons why radio astronomy is super interesting, as it gives us this insight with the redshift And here are some more radio surveys from the VLA and the VLASS. The Very Large Ass. Radio galaxies are particularly bright in hydrogen, yes. There's a lot of hydrogen in the universe. Some folks like Dr. Pierre-Marie Robitaille are trying to explain it and coming up with things like plausible theories. Great imagery here of a, quote, protoplanetary disk, the dusty, dense region around a star possibly forming some planets. That's known as HL Tau. We actually covered that in a previous cosmology segment. Anyway, that's today's cosmology segment. Thanks for tuning in. Once again, congratulations on realizing our channel exists. I've been your host, Dan, a.k.a. smAsho, signing off from the Smash News Network, least busted. Name it news.